Scientists measured the expansion rate of the universe twice, using completely different physics. They expected the same answer. They got two different ones, 9% apart. This gap has now reached 5 sigma certainty, meaning something in our cosmic model is fundamentally broken. In this video, we follow the Hubble tension through the James Webb Space Telescope's failed attempt to solve it. Dark energy changing over cosmic time, phantom energy that grows stronger as space expands, and what the Big Rip means for every atom in existence. Like and subscribe if you want to stay. The universe is breaking its own rules. We begin now. Edwin Hubble pressed his eye to the Hooker telescope in 1929 and found something that would take a century to fully understand. He had expected galaxies to drift in every direction, some moving toward Earth, some moving away, the cosmic equivalent of particles jostling in a room. Instead, every single one was fleeing. In every direction, across every corner of the sky he examined, every galaxy was racing outward from us. And here was the part that truly unnerved him. The farther a galaxy sat, the faster it moved. Distance and speed were linked. The universe was not merely scattered, it was stretching. The implication collapsed inward immediately. If everything was spreading outward from every point, running that motion backward in time would bring all of it together. The universe had a beginning, a moment of creation compressed into a single point. Hubble had not just observed galaxies, he had found the clock that kept cosmic time, and it was ticking. But the clock gave a disastrous answer. The rate Hubble calculated implied a universe roughly 1.5 billion years old. Geologists had already confirmed that certain rocks beneath our feet were 3 billion years old. The universe, by this measurement, was younger than the planet sitting inside it. Either the rocks were wrong, or Hubble was wrong, or something fundamental about the calculation had gone sideways. Astronomers spent decades hunting for the error. Perhaps the distances to distant galaxies had been measured incorrectly. Perhaps the light from those galaxies behaved strangely across such vast scales. A young physicist named George Gamow joked that the early universe had been clogged with fog that slowed light, twisting every inference about speed and distance. It was a joke, but it spread through the cosmology community because people were genuinely desperate for an explanation. The stakes were that high. Better instruments gradually pushed the estimated age upward. By the mid-20th century, the universe was old enough to contain the rocks on Earth, and the sharpest crisis faded. But the deeper discovery held. Space itself was expanding. Galaxies were carried outward by the stretching of the very fabric that held them, like dots on the surface of an inflating balloon. They were not traveling through space. Space was growing around them. This rate of stretching received a name, the Hubble constant. It became the single most important number in all of cosmology. Every other figure in our model of the universe connected to it. The age of the cosmos, the amount of dark matter threaded through the large-scale structure of galaxies, the proportion of dark energy governing the ultimate fate of everything. Pin down the Hubble constant with precision, and you could read the whole story of the universe from a single equation. Astronomers built new telescopes. They launched instruments into orbit. They refined their techniques across decades, reducing the uncertainty from 50% down to barely 1%. The precision improved steadily, and with each improvement came confidence that the mystery was nearly solved. And then the precision itself became the crisis. Two completely independent methods now measured the Hubble constant with extraordinary accuracy. They used different physics, different instruments, different starting points across cosmic history. They produced answers that disagreed by 9%. 9% sounds modest, but at this level of precision, 9% means something fundamental is broken. The number Hubble discovered in 1929 returned, refined to decimal places, carrying a secret nobody expected. An observatory at night is a cathedral of patience, and the astronomers inside are assembling a structure that took a century to build. They cannot simply aim a ruler at a galaxy a billion light years away. The distances involved have no physical yardstick that spans them. Instead, scientists build outward step by step, each measurement calibrated by the one below it, each rung reaching farther into the void. This is the cosmic distance ladder, and it is the most precisely constructed measurement chain in the history of science. The first rung began with a discovery in 1912, when Henrietta Swan Leavitt noticed something remarkable about a class of pulsating stars called Cepheid variables. These stars brighten and dim in regular cycles, and the length of the cycle is precisely linked to the star's true luminosity. Measure the pulse, know the true brightness, compare that to how bright the star appears from Earth, and you have its distance. It was the first reliable cosmic yardstick, and it still anchors everything that follows. The second rung requires catastrophe. Certain types of exploding stars, white dwarf stars that accumulate material from a companion and eventually detonate, always reach nearly the same peak brightness when they go off. Find one of these explosions in a distant galaxy, measure how faint it appears from Earth, and the distance follows from a simple calculation. The chain holds because nearby galaxies contain both Cepheid variables and these standard explosions, letting astronomers cross-calibrate the two methods before leaping to greater distances. Each rung depends on the rung below it, which means an error anywhere in the chain propagates upward through everything. The supernova H0 for the equation of state of dark energy team, led by Nobel laureate Adam Riess of Johns Hopkins University, spent 2 decades refining every link in this chain. They anchored the base of the ladder with 4 independent geometric measurements, each derived from different physics. Cepheid parallaxes measured by the Gaia satellite, eclipsing binary stars in nearby galaxies, and a galaxy called NGC 4258, where clouds of water molecules orbit a central black hole and broadcast their motion in precisely measurable radio signals. Their 2022 result, published after years of cross-checking, measured the expansion rate of the universe at 73 kilometers per second for every roughly 3 million light-years of distance between galaxies. The uncertainty was less than 1.5%. After decades of labor, the distance ladder had spoken. But here is where the story fractures. A completely different method, using the oldest light in existence rather than nearby stars, produced an answer of 67 kilometers per second for the same separation. The two methods disagreed by 9%. Both claimed precision below 2%. The gap between them had grown to 5 sigma, meaning the probability of this discrepancy arising from random chance alone is less than 1 in 3.5 million. The ladder was built from light crossing billions of light-years of space. The competing method was built from the faint glow of the universe's infancy. Both were constructed from completely different materials by completely different teams using completely different tools, and yet they pointed to 2 irreconcilable answers about the same universe. The question of which one was right, or whether both were missing something deeper, was about to become the most contested problem in modern science. Roughly 380,000 years after the Big Bang, the universe crossed a threshold that changed everything. Before that moment, space was a churning plasma of charged particles and light, so dense and hot that photons could not travel more than a tiny distance without being absorbed. The universe was opaque, sealed. Then it cooled enough for electrons and protons to combine into neutral hydrogen atoms, and the barrier lifted. Light streamed freely for the first time in cosmic history. That ancient glow has been traveling ever since, stretching as space expanded beneath it, fading from visible light down through infrared and microwave frequencies, until today it fills the entire sky at a temperature barely above absolute zero. This is the cosmic microwave background, and it is the most information-dense object in cosmology. The European Space Agency's Planck satellite mapped this ancient light across the entire sky with extraordinary precision. The map looks like a sphere covered in faint temperature variations, patches slightly warmer or cooler than average by roughly 1 part in 100,000. Those variations are the fingerprints of sound waves that rippled through the primordial plasma before recombination froze them in place. They carry the memory of the first 380,000 years of existence, encoded in the shape and scale of the fluctuations. And here is the critical insight. Before recombination, sound waves traveled through the hot plasma at a known speed. The distance those waves managed to travel before the plasma cooled and froze represents a fixed physical scale. When astronomers measure the angular size of the fluctuation patterns on the sky, they are measuring how big that frozen wave scale appears from 13.8 billion light-years away. Combine angular size with known physical scale, and geometry gives you the universe's expansion history. The calculation is extraordinarily sensitive. The cosmic microwave background encodes the universe's composition with breathtaking precision. The fraction that is ordinary matter, the fraction that is dark matter, the fraction that is dark energy. These numbers are not rough estimates. They are measurements precise enough to carry 6 significant figures. Feed those values into the standard cosmological model, evolve the universe forward through nearly 14 billion years, and the model predicts what the expansion rate should be today. That prediction, 67 kilometers per second for every roughly 3 million light-years of separation. The uncertainty is barely half a unit in either direction. The precision is staggering. The Planck satellite spent 4 years mapping the sky, and its answer has held up to every independent check since. The disagreement with the distance ladder is catastrophic. The late universe says 73. The early universe says 67. Both sides claim precision below 2%. The gap between them has reached 5 sigma. In particle physics, 5 sigma is the threshold for declaring a discovery. Here, it is the threshold for declaring a crisis. 2 independent methods, 2 completely different strategies, 2 irreconcilable answers. Either one of them hides a systematic error that decades of checking have failed to find, or the universe obeys different rules than the ones written into the model. The echo of creation and the light of nearby galaxies are telling 2 different stories, and so far, nobody can explain why. The crisis was about to become impossible to contain privately among scientists. It was headed for the conference stage, and the moment it arrived there, everything changed. The conference room in 2019 was quiet in the way that rooms go quiet when something unprecedented is happening. Slide after slide showed the same result. Every known systematic error had been examined and eliminated. Every calibration had been cross-checked. Every assumption about how starlight behaved across intergalactic distances had been scrutinized, and still the gap remained, sharp and undeniable. The discrepancy between the 2 methods of measuring the universe's expansion rate had reached 5 sigma. In science, that number carries a specific meaning. It means the probability of the result being a random fluctuation is less than 1 in 3.5 million. 5 sigma is supposed to mean discovery. Here, it meant disaster. Adam Riess stood at the front of the room. He had shared the Nobel Prize in 2011 for co-discovering that the universe's expansion was accelerating, a finding that revealed dark energy and completed what seemed like a triumphant, standard model of cosmology. That model had survived 6 decades of tests. It had predicted the abundance of helium formed in the first minutes after the Big Bang. It had predicted the acoustic peaks in the cosmic microwave background before those peaks were measured. It had predicted the large-scale web of galaxy clusters. It had been right about everything. Now Riess was presenting a measurement that threatened to break the model it had helped build. The implications spread through the community with visible speed. If the tension was real, something fundamental was wrong with the picture of the universe that physics had constructed over 60 years. Not merely incomplete. Wrong. The kind of wrong that required rewriting equations. The skeptics emerged quickly, as they should. Perhaps the Cepheid variable measurements still harbored hidden biases. Perhaps the standard candle explosions used at greater distances behaved slightly differently depending on the age or chemical composition of the stars that produced them. Perhaps multiple unresolved stars were blending together in telescope images, making certain calibration stars appear brighter than they truly were, and therefore closer than they truly were. Each objection received careful study. Each check found nothing. The Cepheid period luminosity relationship held consistently across multiple galaxies with different compositions. The explosion light curves behaved uniformly across cosmic time. The four independent geometric anchors at the base of the distance ladder agreed with each other. The treatment of dust, the calibration of detector sensitivity, the statistical handling of outliers in the stellar samples, all of it was scrutinized. Systematic error after systematic error was eliminated, and the tension refused to dissolve. By 2021, the crisis was impossible to dismiss. Scientific papers multiplied at an accelerating rate, proposing new physics to bridge the gap, a hypothetical form of dark energy active only in the early universe, modifications to how gravity operates on cosmic scales, additional species of particles that might have existed before the universe cooled enough for atoms to form. The cosmological community divided into two camps: those who believed new physics was required, and those who were certain a hidden error must still be waiting to be found. Both camps had credible scientists. Both had compelling arguments. The universe was refusing to settle the argument on its own. Neither camp showed any sign of backing down. Something was going to have to give, and the next development came from an unexpected direction. A scientist who thought both sides might simply be wrong. Wendy Friedman had spent her career measuring cosmic distances, and she was not convinced the crisis was as severe as the headlines claimed. Friedman, based at the University of Chicago, had led the original Hubble Space Telescope key project that first nailed the expansion rate to roughly 72 kilometers per second per unit distance in 2001. She had watched the Hubble tension grow louder and sharper through the subsequent decade, and where others saw a definitive break in physics, she saw something older and more familiar: underestimated uncertainty. Her Carnegie-Chicago Hubble program championed an alternative measurement method called the tip of the red giant branch. The logic behind it is elegant. When a low-mass star exhausts the hydrogen in its core, it swells into a red giant. At the precise moment helium ignition begins in the core, the star's brightness reaches a sharp, physically predictable maximum. This brightness peak appears as a distinct discontinuity in a galaxy's stellar color diagram, and because the physics governing it are well understood, the feature functions as a reliable standard candle. The method carries real advantages. It requires only a single observation epoch rather than months of monitoring. It suffers less from the dust that dims and reddens starlight between galaxies. It avoids the crowding problems that might affect pulsating stars in dense stellar fields. It applies to all galaxy types regardless of their orientation, unlike Cepheid measurements that can be complicated by viewing angle. Friedman's team had built it into a precision tool over more than a decade, testing it across a carefully selected sample of nearby galaxies where the distances could be independently verified. Her 2019 results sat squarely between the two warring camps. The expansion rate, by her team's measurement, was 69.8 kilometers per second per unit distance. This put her only 1.2 sigma from the Planck satellite's early universe answer of 67, and only 1.7 sigma from the distance ladder's answer of 73. She argued that the true Hubble constant might lie in the middle, that both extreme measurements suffered from systematic errors the respective teams had not fully accounted for. The field listened carefully. Then the James Webb Space Telescope arrived, and everything became more complicated. Friedman's team analyzed their data and, in early 2024, believed they had done it. They thought their James Webb measurements had erased the tension entirely, producing a result consistent with the early universe prediction. Then errors surfaced in the analysis. A crowding correction had been applied twice. The statistical uncertainties grew larger when more stars were included. Correcting these issues pushed the values upward, and the gap reopened. Her final James Webb results showed the tip of the red giant branch method giving 69.85, Cepheid variables giving 72.05, and a third method using carbon-rich giant stars called J-region asymptotic giant branch stars giving 67.96. Averaged together, The answer sat near 70. Still between the two camps, but trending toward the higher end, and the error bars were not small enough to declare the tension resolved. The middle position was quietly fading. Every new measurement pushed Friedman's intermediate result a little closer to the high end, and what was about to arrive from orbit would remove the last hope that the whole disagreement could be written off as a measurement artifact. On Christmas Day 2021, a rocket climbed away from the Guiana Space Center in South America, carrying the most expensive scientific instrument ever built. The James Webb Space Telescope had been in development for 3 decades. Its golden mirror, spanning 21 feet across 18 hexagonal segments, was designed to collect infrared light from the edges of the observable universe. Its price tag exceeded $10 billion. Its launch had been delayed so many times that the cosmology community had spent years alternating between anticipation and frustration. The mirror had to unfold in deep space, a sequence of over 300 critical mechanisms, every one of which had to work perfectly. Now, finally, it was in the air, and over the following weeks, every deployment step succeeded. For the Hubble tension, the telescope offered a specific and testable promise. The central suspicion was crowding. Here is the problem. Cepheid variable stars, the pulsating giants used as distance markers, live in the dense, bustling neighborhoods of their host galaxies. Distant galaxies appear small in telescope images. At far enough distances, multiple stars blur together into a single point of light. If a faint companion star happened to overlap with a Cepheid in the image, the combined light would make the Cepheid look brighter than it truly was. A brighter, apparent Cepheid implies a closer galaxy. A closer galaxy, when used to calculate the expansion rate, yields a higher Hubble constant. The effect should grow with distance. Nearby Cepheids, resolved clearly against uncrowded backgrounds, would be measured accurately. Distant Cepheids, suffering more blending, would be systematically biased. If crowding explained the tension, the Hubble constant derived from progressively more distant galaxies should gradually drop when observed with sharper instruments. The James Webb Space Telescope offered roughly 2.5 times the angular resolution of the Hubble Space Telescope in the near-infrared, where Cepheids shine brightest. It also operated at wavelengths where dust became nearly transparent, removing another potential source of bias. If companion stars were contaminating the Cepheid measurements, Webb would find them. The supernova H0 for the equation of state of dark energy team aimed Webb at more than 1,000 Cepheids across 6 galaxies. These galaxies spanned the full range of distances used to calibrate the expansion rate, including 5 galaxies that had hosted 8 of the standard candle explosions anchoring the outer rungs of the distance ladder. The observations were meticulous and the analysis thorough. The data came back in early 2024. What the telescope found was unexpected in a way nobody had hoped for. The Cepheid measurements became sharper, cleaner, and far more precise. The scatter in the period luminosity relationships dropped by more than half. Individual Cepheid precision improved from 20% down to 7%. These were extraordinary gains. The distances did not change. Webb and Hubble agreed to within 1/100th of a magnitude across every galaxy in the sample. No trend appeared with distance. No evidence of crowding bias emerged at any scale. The hypothesis that had offered the most credible escape from new physics was about to receive its formal verdict. In February 2024, the supernova H0 for the equation of state of dark energy team unblinded their full James Webb Space Telescope analysis, and the last serious systematic error candidate died. The team had spent 2 decades searching for the mistake that would explain why their measurement disagreed with the cosmic microwave background. They had examined their calibration chains, their distance anchors, their treatment of dust, their assumptions about how Cepheid variables behave across galaxies with different chemical compositions. Each check returned the same answer. Each avenue of potential bias, when investigated, turned out to be a dead end. Crowding was the final hope, and now the data was in. The comparison was precise. James Webb measurements of more than 1,000 Cepheids against Hubble measurements of the same stars. The formal difference between the two instruments, averaged across all 6 galaxies and the full range of distances tested, minus 0.01 magnitudes, with an uncertainty of plus or minus 0.03 magnitudes, 0. Within the noise of the measurement, the two telescopes agreed perfectly. The team searched for any trend with distance that would indicate crowding bias growing as galaxies receded. They found none. The crowding hypothesis was rejected at 8.2 sigma confidence, a number that exceeds the statistical significance of the Hubble tension itself. The instrument designed to find the error found nothing. Adam Riess spoke to the press. With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe. He said it plainly, without drama, because the data left no room for drama. The systematic error hunt was over. Some researchers held out for other possibilities. Perhaps the standard candle explosions behave differently between nearby and distant galaxy samples in subtle ways. Perhaps the geometric anchors at the base of the distance ladder harbored biases not yet detected. These objections were raised seriously and received serious investigation, but they faced mounting difficulty. Multiple independent methods measuring the local expansion rate using completely different physics continued to cluster around the same higher value. Gravitational lensing time delays agreed with the distance ladder. Surface brightness fluctuations of distant galaxies agreed with it. Planetary nebula brightness functions agreed with it. The consistency of these independent techniques, each one blind to the systematic errors of the others, was becoming nearly impossible to explain as coincidence. A combined study published in December 2024 drew together data from multiple research teams, including the Carnegie-Chicago Hubble program and the Supernova H0 collaboration. All galaxies observed by James Webb yielded an expansion rate of 72.6 kilometers per second per unit distance, nearly identical to the Hubble Space Telescope's answer of 72.8 for the same galaxies. The tension was confirmed. The error explanation was gone. What remained was something stranger, and nobody had a clean answer for it yet. A blackboard filled with equations is less dramatic than a supernova, but sometimes a blackboard is where the most terrifying discoveries live. The Friedmann equations govern how the universe expands. They connect the expansion rate to the age, density, and curvature of the cosmos. Change the expansion rate, and every quantity linked to it shifts. If the Hubble constant is genuinely 73 rather than 67, the consequences do not stay contained. They propagate outward through every inference cosmology has ever made. Start with the age of the universe. A faster expanding cosmos reached its current size in less time. The standard calculation with 73 yields an age somewhere between 12.8 and 13.1 billion years at the limits of statistical confidence. This is younger than the canonical 13.8 billion years derived from the early universe measurement. And here the crisis deepens into something almost philosophical. Certain ancient stars appear to be older than the universe that supposedly contains them. The star catalogued as HD 140-283, sometimes called Methuselah, is a subgiant roughly 190 light-years from Earth. Its age has been estimated at around 13.5 billion years, with significant uncertainty in both directions, but consistent analyses place it near the boundary or beyond it. Some globular cluster populations, ancient stellar communities orbiting our galaxy, show similar age estimates. A universe that is only 13 billion years old cannot contain stars that are older. Something in the calculation must be wrong. Perhaps stellar evolution models carry hidden errors. Perhaps heavy element abundances in these ancient stars affect their development in ways our models have not captured. Perhaps their distances, and therefore their inferred properties, are slightly off. Each of these is possible, but every attempt to resolve the discrepancy runs into the same wall. Independent methods for dating old stars tend to agree with each other, and they tend to agree that these stars are very old indeed. The age crisis compounds further. A younger universe implies a different balance between dark matter and dark energy than the standard model predicts. Observations of galaxy clusters, the statistical distribution of cosmic structure, and gravitational lensing surveys all favor the values derived from the early universe measurement, not the values implied by 73. Every piece of the model connects to every other piece, and pulling on the Hubble constant pulls everything at once. The sound horizon, the standard ruler etched into the cosmic microwave background, would need to be smaller than the standard model predicts. Big Bang nucleosynthesis, the production of helium and deuterium in the first minutes of existence, would need to proceed differently. The expected abundance of galaxy clusters at great distances would need a mechanism nobody has identified. Every proposed solution introduces a new contradiction. Every patch creates a new tier. The universe was not merely expanding at a different rate than expected. The entire framework used to interpret that rate was under assault from multiple directions simultaneously, and the telescope that was supposed to settle this had just ruled out the simplest escape route. The James Webb Space Telescope control room in March 2024 was full of people who had expected to feel relief. $10 billion. 3 decades of development. A mirror composed of 18 gold-coated hexagonal segments, folded for launch, and deployed flawlessly in the cold of space. The most capable infrared observatory ever built, designed to see through the dust that obscured earlier telescopes, to separate stars that Hubble had blended together, to answer the questions that ground-based instruments could not reach. For cosmologists studying the Hubble tension, Webb had represented something specific, the last best test of whether the problem was in the measurements. The crowding hypothesis was elegant and plausible. If companion stars were contaminating Cepheid photometry, Webb would reveal them. If the distance ladder was biased by resolution limits, the sharpest infrared eyes ever launched would show it. The data came back clean. Not clean in the sense that nothing was learned. The James Webb measurements were a remarkable improvement over Hubble in precision, in scatter, in the sheer resolution of individual stellar populations in distant galaxies. But clean in the sense that the distances did not change. Clean in the sense that the bias the community had hoped to find was absent at better than 8 sigma confidence. The psychological impact on the field was profound and uneven. Some researchers had structured years of work around the expectation that Webb would find the error. Graduate students had chosen dissertation topics based on the assumption that the tension would fade. Senior scientists had built reputations on claims that the crowding effect was responsible. The field had been waiting for Webb to deliver a verdict, and the verdict arrived. The distance ladder was right, and the problem was still unsolved. The standard model of cosmology, known as lambda cold dark matter, had survived every test thrown at it for 6 decades. 6 parameters, adjusted to fit the available data. And from those 6 parameters, the model had predicted the cosmic microwave background acoustic peak structure before it was measured. It had predicted the ratio of hydrogen to helium produced in the first minutes of the Big Bang. It had predicted the accelerating expansion years before it was confirmed by supernova observations. It was the most successful predictive framework in the history of physics. And now it could not reconcile 2 measurements of its most fundamental parameter. The expansion rate of the universe, measured from the early cosmos, said 67. Measured from the late cosmos, it said 73. James Webb had verified the late measurement. The early measurement rested on a satellite's analysis of the oldest light in existence, checked and rechecked for a decade without finding a flaw. Both could not be right. The model that connected them could not be correct as written. Something in the equations governing 13.8 billion years of cosmic evolution was missing or wrong. The field faced this conclusion in early 2024 with a mixture of excitement and dread. Excitement because discovering a flaw in the standard model would be one of the greatest scientific events in a generation. Dread because nobody yet knew what would replace it. Something had to give. The question was what? 5,000 fiber optic cables hang from the Mail telescope at Kitt Peak in Arizona. each one tipped with a small robotic arm that repositions itself every 20 minutes with mechanical precision. The Dark Energy Spectroscopic Instrument is not a telescope in the traditional sense. It is a light-gathering machine of extraordinary reach, designed to map the three-dimensional positions of tens of millions of galaxies spread across billions of light-years of space. Every night it opens, it records the spectra of roughly 100,000 galaxies, measuring how fast each one moves away from Earth and where it sits in the cosmic web. Over 5 years, the instrument will have observed more than 40 million objects, producing the largest map of large-scale structure ever assembled. Its target is a signal frozen into that structure from the very beginning of time. Before the universe cooled enough for atoms to form, sound waves rippled outward through the hot plasma that filled all of space. These waves were driven by the interplay between the pressure of radiation and the gravity of matter, oscillating outward from dense regions, carrying energy in every direction. When the universe cooled and the plasma froze into neutral hydrogen, those waves stopped. The distances they had traveled became locked into the statistical distribution of matter, and that imprint is still visible today in how galaxies cluster. Galaxies are slightly more likely to be separated by a specific distance than by slightly smaller or larger distances. The preferred separation corresponds to how far those ancient sound waves traveled before everything froze. By measuring how this preferred scale changes with redshift across cosmic history, the Dark Energy Spectroscopic Instrument traces how the universe has expanded over billions of years, rung by rung through time. In April 2024, the instrument released its first major results. The baryon acoustic oscillation signal was detected clearly across multiple redshift ranges, confirming the standard cosmological model's predictions in broad outline. The expansion history followed lambda-cold dark matter's expected shape, but then the collaboration combined their data with the cosmic microwave background and with observations of standard candle supernova explosions, and something appeared that nobody had expected. The combined datasets preferred a dark energy equation of state that differed from a simple cosmological constant. The standard model treats dark energy as a fixed quantity, an energy density woven permanently into the fabric of space, identical everywhere and unchanging through time. Einstein introduced it as a cosmological constant. The data suggested it might be anything but constant. The statistical preference was modest, only 2.6 sigma, dependent on which supernova dataset was included. It could have been a fluctuation, but it pointed clearly in one direction: dark energy that was stronger in the past and weaker today. Dark energy that evolves. Dark energy that is not a constant at all. The Hubble tension had been a problem of two measurements disagreeing. This was something different. This was the force driving cosmic expansion itself, behaving in ways the model could not accommodate. What came next would make everything that had come before seem like a quiet prologue. March of 2025. A team of scientists in Arizona stares at 3 years of collected light. The Dark Energy Spectroscopic Instrument, 5,000 robotic fiber optic eyes mounted on a telescope atop Kitt Peak, has spent 36 months doing one thing: mapping where galaxies sit in space. It records the precise color of each galaxy's light, how much the universe has stretched that light since the galaxy sent it out. From those stretches, the instrument reconstructs the three-dimensional skeleton of the cosmos across billions of light years. 14 million galaxy spectra, 836,000 quasar spectra, 3 years of desert nights. When the collaboration finally unlocks their own data and examines the results, the answer is not what anyone hoped to hear. The imprint of ancient sound waves, frozen into the spacing of galaxies across the sky, tells a story about how the universe expanded at different points in its history. Those sound waves rippled through the hot plasma of the early cosmos before recombination locked them in place. Now they show up as a subtle preference for galaxies to cluster at a particular separation. That preferred distance changes with cosmic epoch, and by tracking how it changes, scientists can reconstruct the entire expansion history of the universe. And the expansion history the instrument finds disagrees with what a simple, constant dark energy would produce. The cosmological constant is the term Einstein added to his equations of gravity to describe dark energy. It represents a fixed, unchanging energy woven into the fabric of empty space itself. Every cubic inch of the void holds the same amount of it, always, at every moment in cosmic history. This constant is the foundation on which the entire standard model of cosmology rests. The dark energy spectroscopic instrument data says it may not be constant at all. When combined with microwave background measurements from the Planck satellite, the Year 3 results show a preference for evolving dark energy at 3.1 sigma confidence. When the collaboration adds supernova data from the Dark Energy Survey, the preference climbs to 4.2 sigma. 4.2 sigma means that if dark energy were truly constant, a measurement this far off would occur by chance in roughly 1 in 50,000 experiments. Something is drifting. The best fit model describes dark energy that was stronger in the past and is weakening today. In the technical language of cosmology, the equation of state parameter sits near -0.75 now, and its past behavior traces a path that crossed below -1 into a regime physicists have long considered physically troubling. Mark Kamionkowski at Johns Hopkins University, one of the architects of modern cosmological theory, later described the moment in interviews as transformative. Dark energy had always been mysterious, but at least static. A drifting dark energy opens entirely new territory. Dark energy spectroscopic instrument director Michael Levi noted that theorists were producing roughly 3 new papers per day responding to these results. 3 papers per day. Because the implications do not stop at the Hubble tension. A changing dark energy does not merely explain why local measurements of expansion differ from early universe predictions. It threatens to rewrite what we thought we knew about the age of the cosmos, the future of all structure, and the ultimate fate of everything that exists. And the direction it is drifting points somewhere deeply unsettling. Every physicist in the room understands what the equation means, and almost none of them want it to be true. Dark energy with a constant equation of state of -1 carries the universe toward a slow, cold dispersal. Galaxies drift apart over trillions of years, stars burn out. The cosmos cools toward absolute stillness, peaceful in a cosmic sense. The technical term is heat death, and for a long time it seemed like the most likely conclusion to the story of everything. But the dark energy spectroscopic instrument data hints at something different. The preferred values of dark energy behavior place its past character in what physicists call the phantom regime, where the equation of state dips below -1, and phantom dark energy does not carry the universe toward stillness. It accelerates, without limit, toward destruction. Here is what makes phantom energy strange. Normal matter dilutes as the universe grows. Pour energy into a larger box, and the density drops. But phantom dark energy works in reverse. As the universe expands, phantom dark energy grows denser. The larger space becomes, the more energy space itself contains, and more energy means faster expansion. Faster expansion means even more energy. The cycle feeds itself until it reaches a finite time singularity. That singularity has a name. In their 2003 paper in Physical Review Letters, Robert Caldwell, Mark Kamionkowski, and Nevin Weinberg calculated what a Big Rip timeline would look like for a universe with phantom dark energy strong enough to matter. The schedule is worth sitting with. Roughly 60 million years before the final singularity, the expansion overcomes gravity on the largest scales. Galaxy clusters dissolve. The gravitational bonds that hold collections of thousands of galaxies together snap under the relentless pull of accelerating space. The members of those clusters scatter into the void, never to interact again. 3 months before the end, the force tears apart solar systems. Planets lose their orbits. The gravitational grip that has held worlds in circular paths for billions of years becomes insufficient against the swelling of space. 30 minutes before the singularity, Earth explodes. The binding energy of rock and ocean and atmosphere fails against expansion that now operates on planetary scales. 10 to the minus 19 seconds before the end, atoms themselves are torn apart. Then nothing. Now pause on this important distinction. The dark energy spectroscopic instrument data do not confirm we are headed for a big rip. That needs to be stated clearly. The preference for past phantom behavior stands at roughly 3 to 4 sigma depending on the dataset used. Other mathematical descriptions of the same data avoid phantom behavior entirely. The null energy condition, which phantom dark energy violates, may be a hard physical law that the universe respects absolutely. But the possibility is no longer purely theoretical. It is on the table, fed by real observations from real instruments measuring real galaxies across real distances. And here is the part that should recalibrate how you think about everything that follows. The same data producing this possibility also disagrees with the standard model of cosmology in ways that connect directly to the Hubble tension. The same force whose nature we cannot pin down is the force responsible for the expanding universe in the first place. Everything is connected, and the connection is about to get far more complicated. Not every scientist accepts the crisis as real. In conference halls and on preprint servers, a persistent and serious group of researchers argues that the Hubble tension reflects measurement errors rather than new physics. Their position is scientifically legitimate and deserves honest examination, because if they are right, everything described in the previous chapters dissolves into a calibration problem. The skeptic's case rests on the structure of the distance ladder itself. The ladder involves multiple steps, each calibrated by the one below it. Cepheid variables must be anchored to geometric measurements. Those geometric measurements carry uncertainties that propagate upward through every rung. Type Ia supernovae must be standardized using assumed relationships between their brightness, their color, and the rate at which they fade. The choice of which supernovae to include, which to exclude as outliers, and how to correct for dust between the stars affects the final answer in ways that are difficult to quantify. In 2023, Daniel Skolnick and colleagues analyzed how different teams handle the same supernova data and found that different treatment choices scatter the results across a range large enough to be concerning. The distance ladder is not a single measurement. It is a set of choices, and the choices matter. Wendy Friedman of the University of Chicago has made this argument more carefully than anyone. She has spent her career on cosmic distance measurements. She led the original Hubble Space Telescope key project that produced the first refined determination of the Hubble constant around 72 in 2001. When the tension emerged, she championed alternative methods that might reveal hidden errors. Her tip of the red giant branch measurements consistently find intermediate values, around 69 to 70. She argues that both extremes, the 67 from the cosmic microwave background and the 73 from the SH0ES team, may harbor underestimated systematic errors. The true value might sit between them, and the apparent tension might be inflated by overconfidence in both camps. The history of science provides ammunition for caution. The solar neutrino problem persisted for decades before neutrino oscillations explained the apparent deficit. The accelerating expansion of the universe was initially doubted and required years of confirmation before being accepted. Anomalies frequently dissolve when measurements improve. But here is where the skeptic's argument runs into trouble. The James Webb Space Telescope verification of the Cepheid calibration removed the most plausible candidate for systematic error: gravitational lensing time delays, using completely different physics and a completely different set of assumptions, yield a high Hubble constant. Surface brightness fluctuations, a method measuring the granularity of galaxy light, yield a high value. Planetary nebula luminosity functions yield roughly 74. These methods share essentially no systematic errors with each other or with the distance ladder. They use different physics, different objects, different instruments, different analysis techniques. They agree. When 5 independent measurements, using 5 different physical phenomena, all point in the same direction, dismissing their conclusion as coincidental systematic error requires extraordinary evidence. The skeptic may still be right. Science demands we take the possibility seriously. But the burden of proof has shifted. The null hypothesis that everything is fine requires its own defense now. In a physics office in 2019, 4 theorists wrote down an equation that seemed to solve everything. Vivian Poulin, Tristan Smith, Tanvi Kawal, and Mark Kamionkowski proposed what they called early dark energy. The idea was elegant and targeted. The problem with the Hubble constant is that 2 methods disagree. The early universe predicts a slow expansion rate, and the late universe measures a fast one. If you could add energy to the early universe without disturbing everything else, you could bring the 2 measurements into alignment. The mechanism works through the sound horizon. That horizon is the distance sound waves traveled through the hot plasma of the young universe before recombination froze them in place. It serves as the fundamental ruler used to interpret the cosmic microwave background. The Planck satellite measures the angular size of features in that ancient light. Knowing how big those features physically were, by knowing the sound horizon, converts that angle into a measurement of the Hubble constant. Smaller sound horizon, larger Hubble constant. Early dark energy proposes that a new field existed briefly around the time matter and radiation were equal in density, roughly 1,000 years after the Big Bang. This field added energy to the early universe, increasing the expansion rate before recombination. Faster early expansion compressed the sound waves into a smaller scale before they froze. The smaller scale, interpreted through the cosmic microwave background, demands a larger Hubble constant. The early universe measurement rises towards 73, and the tension dissolves. The proposal swept through theoretical cosmology. Hundreds of papers followed, refining the model, extending it, testing its variants. It became the consensus frontrunner for new physics beyond the standard model, but problems accumulated. The field requires fine-tuning. The amount of early dark energy and the precise moment it activates must be chosen very carefully to resolve the Hubble tension without creating new discrepancies elsewhere. This kind of precision looks less like a natural feature of the universe and more like a parameter adjusted to match a measurement. Worse, early dark energy tends to worsen a separate problem called the Cepheid tension, a disagreement between predicted and observed levels of matter clustering. Fixing the Hubble constant by adding early dark energy typically pushes matter clustering predictions even further from observations, and the observational constraints are tightening. A June 2025 analysis combined data from the Planck satellite, the Atacama Cosmology Telescope, and the Dark Energy Spectroscopic Instrument. The conclusion was blunt: no evidence for early dark energy. The fraction of cosmic energy the field could contribute was constrained below 9% at 95% confidence. The proposal that once seemed poised to resolve the greatest crisis in cosmology is failing its tests. Theorists are still working to find a version that survives, but the leading candidate is wounded, and nothing has stepped in to replace it. Something in the cosmos is broken. The fix everyone hoped for is not arriving. The universe is clumping wrong. That sentence requires some unpacking. The standard model of cosmology makes precise predictions about how matter should cluster under gravity over cosmic time. Starting from the nearly smooth conditions visible in the cosmic microwave background, cold dark matter pulls ordinary matter together into filaments, walls, and nodes, forming the cosmic web. Galaxy clusters assemble at the densest nodes. Vast, empty voids stretch between the filaments. The parameter physicists use to measure how strongly matter clumps is called Cepheid. It combines the amplitude of matter density fluctuations with the square root of the ratio of total matter density to critical density. The name is technical, but the concept is straightforward. Cepheid measures how lumpy the universe is compared to how lumpy gravity predicts it should be. Multiple independent surveys have measured Cepheid by observing how light bends around large structures. This technique, called weak gravitational lensing, probes the total mass distribution in the universe, including dark matter that emits no light. The results consistently find that the universe is smoother than predicted. The Kilodegree survey in Chile, the Dark Energy survey in the same mountains, the Hypersuprime Cam survey in Hawaii. Different telescopes, different fields of sky, different analysis pipelines. All of them measure a universe that clusters about 2 to 3 sigma less vigorously than the standard model expects. The Hubble tension says the universe is expanding too fast. The Cepheid tension says it is clumping too slowly. These are separate failures, and their coexistence points toward a common underlying cause. Here is the problem that makes this genuinely alarming. Many proposed solutions to the Hubble tension make the Cepheid tension worse. Early dark energy is the clearest example. Adding energy density to the early universe increases the amplitude of matter fluctuations, pushing Cepheid higher and further from observed values. A theory that resolves the expansion problem while worsening the clumping problem is not a solution. Any complete theory of physics beyond the standard model must explain both tensions simultaneously. This requirement is severe. The parameter space of viable solutions shrinks dramatically when both constraints apply at once. Modified gravity theories are among the few frameworks that could potentially address both problems at the same time. If gravity behaves differently on the largest cosmic scales than on the scales of galaxies and solar systems, it could simultaneously change the expansion history and suppress structure formation. But no modified gravity theory has passed all observational tests yet. Dark matter that interacts with itself or with dark energy could also address both tensions in principle. Small adjustments to how dark matter behaves over cosmic time change both the expansion rate and the growth of structure. What this chapter establishes, confirmed by multiple independent observations, is that the crisis is wider than the Hubble constant alone. The universe is failing the standard model from at least 2 different directions. Whatever physics lies beyond the standard model must be capable of solving both problems at once. That constraint will be essential in what comes next. For 100 years, Einstein's general relativity has described gravity with almost miraculous accuracy. It predicted the bending of light around massive objects before the measurement was made. It predicted the existence of gravitational waves, detected a century later. It described the precession of Mercury's orbit, calculated the delay of radio signals passing near the star at the center of our solar system, and anchored the entire global positioning system through corrections for time dilation that would render navigation useless without them. On every scale, where it has been tested directly, general relativity passes, but there is a scale where it has barely been tested at all, the scale of the entire observable universe. On distances of billions of light years and timescales of billions of years, we do not have direct experimental tests of whether Einstein's equations hold exactly. We have observations, and we fit models to those observations. The model that fits best has been lambda cold dark matter. But lambda cold dark matter is now cracking. Modified gravity theories propose that Einstein's equations are an approximation that holds on small scales but breaks down on the largest cosmic scales. The breakdown would change the relationship between matter and geometry, altering how the universe expands and how structure forms within it. The simplest class of modified gravity theories extends Einstein's framework by adding functions of the curvature scalar. These theories, called f of r gravity, reduce to general relativity in dense environments through a mechanism called screening, which suppresses the modifications near massive objects. This is why solar system tests would still be passed. Only in the thin, low-density expanses between galaxy clusters would the modifications become significant. Erik Verlinde at the University of Amsterdam proposed a more radical departure. His emergent gravity theory derives gravitational effects from thermodynamic principles and quantum information, treating gravity as a consequence of how matter displaces entropy rather than as a fundamental force. In this framework, the phenomena attributed to dark matter and dark energy emerge naturally from the underlying information structure of space, without invoking unseen components. Verlinde's proposal faces serious challenges matching observations of the cosmic microwave background, but subsequent refinements have improved its performance. It remains a minority position, but it illustrates how far theorists are willing to go. The appeal of modified gravity for the twin tensions is clear. If gravity itself operates differently on cosmological scales, the expansion history and the growth of structure change together. The same modification that raises the local Hubble constant could simultaneously suppress matter clustering, addressing both problems with a single mechanism. But no modified gravity theory has succeeded. The combination of cosmic microwave background precision, baryon acoustic oscillation measurements, gravitational lensing surveys, and supernova observations imposes constraints so tight that proposed theories struggle to satisfy them all simultaneously. Every time a modification resolves one measurement, it fails another. The ring is crowded, modified gravity is in it, but it has not won the fight yet. What if the problem has nothing to do with the physics of the universe itself, and everything to do with where we happen to be sitting inside it? Picture the cosmos as an enormous sponge. Filaments of galaxies form the solid structure, stretching across hundreds of millions of light years. Between the filaments lie voids, regions where matter is sparse, where galaxies are few, and where the expansion of space proceeds more freely than in the denser surroundings. We live in one of the filaments, or at least, we thought we did. In 2013, 3 astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie published a study of the galaxy distribution within about 1 billion light-years of our own position. They found something unexpected. The region surrounding the local group, the cluster of galaxies that contains our own Milky Way, appears significantly underdense. Matter in the roughly 300 million light-year shell around us is roughly 46% less abundant than the cosmic average. This structure is known as the KBC void. The significance of an underdense neighborhood becomes clear when you think about how local expansion measurements work. Every method that produces a high Hubble constant measures the recession of galaxies relatively nearby within the last few billion light-years. If that local region is emptier than average, matter's gravitational pull on expansion is weaker than usual. Local expansion proceeds faster than the cosmic mean. Local measurements of the Hubble constant would naturally come out high. The early universe measurement, built from the cosmic microwave background, averages over the entire observable cosmos. It would reflect the global expansion rate, which is slower. The two measurements would disagree for a purely geographic reason. We happen to live in a quieter, emptier corner of the universe, and local measurements reflect local conditions rather than the global average. Researchers including Indranil Banik and Pavel Krupa have pursued this explanation using modified gravity frameworks, arguing that a combination of an unusual local environment and alternative gravity physics could simultaneously explain the KBC void and the Hubble tension without invoking any exotic cosmic components. Their best-fitting model explains the observations at roughly the 1% confidence level, meaning some residual tension remains, but the fit is genuinely competitive. The problems with this explanation are equally real. A void of the size and depth needed to fully explain the Hubble tension would itself be statistically unusual within the standard model of cosmology. Lambda cold dark matter predicts voids of this scale should be rare. To explain one tension, the local void hypothesis creates another. Why do we happen to live in such an anomalous location? Anthropic arguments can handle this question in principle. We can only measure the universe from where we stand, and our position may have influenced the conditions that allowed us to exist in the first place. But future surveys will resolve this. Mapping the galaxy distribution to greater distances and higher precision will either confirm the KBC void at the required scale or rule it out. The answer is coming within a decade. Particle physics and cosmology share a long, productive secret. The early universe was the most violent particle accelerator that has ever existed. In the first seconds after the Big Bang, temperatures exceeded anything achievable in Earth-bound laboratories by factors of trillions. Particles far more massive than anything detected at the Large Hadron Collider would have appeared and disappeared in that furnace, leaving imprints in the structure of the cosmos that persist today. The cosmic microwave background, the abundance of light elements forged in those first minutes, and the statistical distribution of galaxies all encode the particle content of the early universe. If new particles exist, the early cosmos may already have told us. One of the most studied possibilities involves what physicists call additional effective neutrino species. Neutrinos are nearly massless particles that interact only through gravity and the weak force. The standard model of particle physics predicts 3 varieties. Cosmological observations have long been consistent with this number, but if additional light particles exist, particles that share the mass and speed of neutrinos but have no other interactions, they would contribute to the radiation density of the early universe as if they were extra neutrino species. This extra density changes the expansion rate before recombination. Faster early expansion compresses the sound horizon and raises the Hubble constant inferred from the cosmic microwave background. This mechanism is similar in outcome to early dark energy, but the physics is entirely different. Instead of a new field, it involves new particles. The effect per additional species is smaller, requiring nearly 1 full extra neutrino equivalent to fully close the Hubble tension, which is more than current constraints comfortably allow. Axions present another candidate. These ultralight scalar fields were originally proposed to solve a different problem in particle physics, the strong charge parity problem, but they carry properties that make them interesting for cosmology. An axion field rolling slowly down its potential can mimic dark energy, contributing a slowly changing energy density that might explain both the current acceleration of expansion and past behavior different from a simple constant. The dark energy spectroscopic instruments' baryon acoustic oscillation measurements impose constraints on neutrino masses that, as of 2025, are approaching tension with the minimum values required by neutrino oscillation experiments. This means the data are pressing against what particle physics already knows must be true. If dark energy is evolving, this particular tension eases somewhat. The layering of tensions is growing deeper. Hubble tension, Sate tension, neutrino mass bounds pressing against particle physics flaws. Multiple independent measurements pulling against each other from multiple directions. Each thread connects to the others. The universe is not failing one test, it is failing many. And the failures cluster around something hidden in the physics of the early cosmos, something that may be speaking through all of them at once. The oldest stars in our galaxy may be part of that message too. There is a star about 190 light-years from Earth that should not exist, formerly catalogued as HD 140,283. It is commonly called the Methuselah star. It is a subgiant, a star slightly evolved from the main sequence, burning the last of its hydrogen before the long process of swelling into a giant begins. It is among the most metal-poor stars known, meaning it formed before generations of supernovae seeded the cosmos with heavy elements. It formed early, very early. Age estimates for this star have hovered around 14 billion years for decades, with substantial uncertainties that depend on assumptions about the star's precise composition, its distance, and the behavior of stellar physics at low metallicity. A 2021 reanalysis using Gaia spacecraft distance measurements reduced the estimate and tightened the error bars, producing a central value closer to 12 billion years with an uncertainty of about 1 billion years. That is somewhat more comfortable. Other globular clusters complicate the picture. Collections of ancient stars in galaxies near our own, measured through multiple independent techniques including main sequence turn-off points and white dwarf cooling curves, consistently suggest ages of 12 to 13.5 billion years. If the Hubble constant is truly 73, as the distance ladder and multiple independent methods suggest, then the universe is only about 12.8 to 13.1 billion years old. The overlap between these ranges is thin. At the edges of their uncertainties, the oldest stellar ages and the universe's age at 73 are consistent. But there is no comfortable margin. The age crisis is distinct from the Hubble tension, but they share a root. Both point toward a universe that is younger than the standard model at 67 would suggest, and they point in different directions for resolution. If stellar ages are correct at 13.5 billion years, the Hubble constant cannot be as high as 73 without invoking new physics that modifies the cosmic timeline. Possible escapes exist. Perhaps stellar models at very low metallicity are systematically wrong. Perhaps distances to the oldest globular clusters are mismeasured. The uncertainties are genuine, and researchers continue working to reduce them. But the convergence of independent stellar methods, spanning different physics from nuclear burning rates to electron capture on white dwarfs to radioactive isotope abundances in stellar spectra, is harder to dismiss as coincidence than a single measurement. Confirmed. The universe has a measured age from the Standard Model and the early universe Hubble constant value of 67. Confirmed. Some of the oldest known stellar populations push toward ages that create tension with a Hubble constant of 73. Unknown. Which constraint will yield when measurements improve further? The stars are not cooperating, and they are not the last independent check that refuses to stay quiet. Light bends. This is not a metaphor. General relativity predicts that massive objects curve the geometry of space, and light follows the curvature. When a galaxy sits almost perfectly between Earth and a distant, brilliant quasar, the galaxy's gravity bends the quasar's light around both sides, producing multiple images in our telescopes. In some geometries, the bending is so complete that the light wraps into an arc or even a full ring. This effect is called gravitational lensing, and it carries a hidden clock. Each path around the lensing galaxy has a different length. Light traveling the shorter path arrives before light traveling the longer path. When the quasar flickers, as quasars regularly do as material falls into their central black holes, that flicker appears first in one image and then, some hours or days later, in the other image. The delay between arrivals depends on the geometry of the entire system. The distances between Earth, the lens, and the quasar, and the distribution of mass within the lensing galaxy. Those distances depend on the Hubble constant. Measure the time delay, model the mass of the lensing galaxy, calculate the geometry, read out a Hubble constant that is entirely independent of Cepheids, supernovae, the sound horizon, and every other method previously discussed. A December 2025 study, led by Kenneth Wong at the University of Tokyo, analyzed 8 gravitational lens systems with well-characterized mass distributions. The collaboration measured time delays with high precision, constructed detailed mass models of the lensing galaxies using observations at multiple wavelengths, and combined the results into a single Hubble constant determination. Their answer sits near 73. It is more consistent with late universe measurements and less consistent with the early universe prediction of 67. This result is significant for a reason that goes beyond the number itself. Gravitational lensing time delays share essentially no systematic errors with the distance ladder. The technique does not use Cepheids or supernovae. It does not rely on calibrating standard candles. It uses only the mass distribution of a galaxy and the geometry of the universe, 2 things that can be measured through completely independent observations. If the Cepheid-based distance ladder suffered from some unknown systematic error that inflated all its measurements, gravitational lensing would detect no such error. It would find a different, lower value. Instead, it finds the same high value. The late universe camp is not a single method finding an anomalous result. It is a growing collection of completely independent techniques using different physics, different objects, and different assumptions, all converging on the same answer. The cosmic microwave background stands alone on the other side. It has extraordinary precision. Its measurements are exquisitely clean. But it is one method, and one method, against a growing chorus of independent confirmation, faces an increasingly heavy burden of explanation. The universe is expanding fast. Every independent check confirms it, and the framework we built to explain the cosmos cannot account for it. What remains is genuinely new. A new project lands in late 2025 with a simple, alarming premise. Every measurement of the Hubble constant might be compromised, and nobody inside the field can see it. The project is called redshift. It is funded by the European Research Council and it borrows a technique from cybersecurity. In digital defense, a red team is a group paid to attack a system. They are not trying to fix it. They are trying to break it. They probe every assumption, every doorway, every hidden corner. If there is a flaw, they will find it, because finding it is the entire job. Ridddle applies that same adversarial logic to cosmology. The team recruits statisticians, machine learning specialists, and observational astronomers who had no previous involvement in Hubble constant measurements. They receive raw telescope data and instructions. Derive the expansion rate yourselves. Do not look at published values first. Question everything. This kind of external audit had never been done before. Cosmology is a field built on trust. Teams share methods, review each other's papers, and check each other's work through the standard peer review process. What Ridddle recognizes is something uncomfortable. The people most qualified to spot an error are often the least likely to find one, because they built the system themselves. Here is what makes this project so significant. By late 2025, the James Webb Space Telescope had already ruled out the last major candidate for a measurement error inside the distance ladder. The crowding hypothesis, the idea that blended stars were inflating the Cepheid brightness measurements, had been eliminated at 8 sigma confidence. Every other systematic that the field could name had been checked and cleared. So either the tension is real, or there is a flaw so subtle and so deeply embedded in the shared assumptions of the community that insiders cannot see it. Ridddle is designed to find that flaw, if it exists. The stakes are not abstract. Careers have been built on lambda-cold dark matter surviving every challenge. Textbooks have been written around it. Graduate students are choosing dissertation topics based on whether they believe the tension is real or illusory. If Ridddle confirms the measurements, the case for new physics becomes nearly impossible to dismiss. If they find something the field missed, the crisis deflates overnight. Early results are expected in 2026, and the community is watching. There is an edge in that anticipation. The Hubble tension has been grinding on for nearly a decade. People are tired of the uncertainty, tired of the competing camps, tired of the conferences where the same arguments cycle endlessly. Ridddle promises something different, a verdict from outside the debate itself. This kind of adversarial verification is rare in science. It signals a mature recognition that the stakes have become too high for standard checks. The community is, in effect, admitting that it cannot trust itself to find its own blind spots. That admission is itself a sign of how serious the situation has become. The red team is in the building, and what they find next may force cosmology to answer a question it has been avoiding. What if the crisis was always real, and everyone was simply too close to see it? Picture a framework so successful it explained everything for 60 years. 6 numbers, a handful of equations, billions of confirmed predictions. That is lambda-cold dark matter, and it is cracking. The model was built on a simple architecture. 6 parameters describe the entire observable universe. How fast space is expanding, how much ordinary matter exists, how much dark matter exists, how transparent the early cosmos was to its own radiation, how uniform the first density fluctuations were, and how large those fluctuations grew. From those 6 numbers, the model predicts the pattern of ancient microwaves, the abundance of helium and deuterium forged in the first minutes, the way galaxies cluster into vast cosmic webs, and the accelerating expansion of space itself. Every test confirmed it. Every observation fit. For 6 decades, lambda-cold dark matter survived everything cosmologists could throw at it. The discovery of dark energy in 1998, which earned the Nobel Prize, was absorbed without breaking the model. The precision mapping of the cosmic microwave background only sharpened its predictions. Then came 2 numbers, 67 and 73. The Planck satellite measures the ancient microwave glow and derives 67 kilometers per second per distance unit. The distance ladder, refined over decades and verified by the James Webb Space Telescope, measures 73. Both claim precision below 2%. Both cannot be correct within a model that assumes a single, consistent expansion history from the Big Bang to today. The lambda cold dark matter model demands that these numbers match. If the same 6 parameters govern the entire history of the universe, then measuring the expansion rate from the early universe and from the late universe must produce identical results. They do not. The gap has exceeded 5 sigma. The chance this is a statistical accident is less than 1 in 3.5 million. This is not just a number problem, it is an internal consistency failure. A model that cannot reconcile its own predictions across different cosmic epochs is a model that is wrong or, at minimum, incomplete. The dark energy spectroscopic instrument results add pressure from a different direction. If dark energy has evolved over cosmic time, as the baryon acoustic oscillation data suggest at more than 4 sigma when combined with certain supernova datasets, then the cosmological constant assumed in lambda cold dark matter is dead. The model requires a 7th parameter, at minimum, and probably a new physical mechanism to generate it. The CERN Courier published its assessment in March 2025 with unusual directness. The next few years will be crucial for understanding the Hubble tension and may decide the fate of the lambda cold dark matter model. Science has been here before. The geocentric universe was overthrown. The static universe was overthrown. The steady-state cosmology was overthrown. Each fall revealed something deeper. But each transition was painful, contested, and slow. The institutions of knowledge do not move easily. Lambda cold dark matter may not be wrong in the way that a mistake is wrong. It may be the way every great framework is wrong, precisely right up to the limits of what it was designed to explain, and precisely insufficient at exactly the boundary where something new begins. Something is coming. The model is telling us so. Everything the cosmic microwave background tells us about the expansion rate depends on a single physical scale. A ruler, frozen into the cosmos 380,000 years after the Big Bang, and if that ruler is the wrong length, every conclusion drawn from it must be revisited. That ruler is called the sound horizon. Before recombination, the early universe was a hot, dense plasma, a churning ocean of matter and radiation so tightly coupled that pressure waves moved through it the way sound moves through air. Those waves propagated outward from density fluctuations, carrying energy in every direction. When the universe cooled enough for neutral hydrogen to form, the plasma froze and the waves stopped. The distance those waves had traveled was permanently imprinted into the structure of matter. That distance, roughly 500 million light-years, is confirmed by independent observation. Galaxy surveys today find that pairs of galaxies separated by approximately that distance are slightly more common than chance would predict. The sound horizon appears as a real statistical bump in the distribution of matter across the sky. It is the same ruler, viewed from 2 completely different directions. The cosmic microwave background measurement of the Hubble constant works like this. The satellite measures the angular size of acoustic peaks in the ancient microwave glow. To convert an angle into a physical expansion rate, you need to know the physical size of what you are measuring. That size is the sound horizon calculated from early universe physics, the densities of ordinary matter, dark matter, and radiation, plus the speed of sound in the primordial plasma. Lambda cold dark matter gives a specific value for the sound horizon based on its 6 parameters. Plug that value into the angle measurement, and you get 67 for the Hubble constant. The calculation is clean. But here is where the crisis cuts deep. If the true Hubble constant is 73, the sound horizon must be smaller than lambda cold dark matter predicts. The same observed angle, divided by a smaller physical ruler, gives a larger expansion rate. The math is straightforward. The implication is not. A smaller sound horizon requires new physics in the early universe. Something must have added extra energy density before recombination, speeding up the expansion just enough to compress the sound waves into a tighter scale. Early dark energy was proposed to do exactly this. But observations from the Dark Energy Spectroscopic Instrument and the Atacama Cosmology Telescope have tightened the constraints so severely that the allowed parameter space for early dark energy has nearly vanished. And the crisis compounds itself. The sound horizon connects directly to Big Bang nucleosynthesis, the process that forged helium, deuterium, and lithium in the first 3 minutes of cosmic history. Those element abundances are observed in the oldest, most pristine gas clouds in the universe, and they match lambda cold dark matter predictions with extraordinary precision. Any modification that shrinks the sound horizon must preserve those abundances. Almost nothing does. Every door appears to close. The tension cannot be an error in the distance ladder. The James Webb Space Telescope confirmed that. The tension cannot be resolved by the most studied theoretical solution. The constraints confirm that. The sound horizon crisis is real, structural, and has no accepted explanation. And that is exactly where the second skeptic has been waiting. This skeptic is different. The first skeptic questioned the measurements. This one questions something deeper, the framework used to interpret them. The 5 sigma threshold for claiming a discovery was developed in particle physics, where experiments at the Large Hadron Collider can run millions of trials, control every variable, and reproduce results at will. 5 sigma, in that context, means something very specific. The same statistical anomaly, encountered once in the only universe we have access to, means something quite different. Cosmology faces what philosophers call the problem of uniqueness. We cannot rerun the Big Bang. We cannot build a second universe and compare it to ours. We have one sample, one history, one sky. The standard frequentist statistics that work beautifully in repeated experiment physics become philosophically strained when applied to the cosmos as a whole. The Hubble tension involves comparing 2 measurements drawn from radically different cosmic epochs. The cosmic microwave background probes physics 380,000 years after creation. The distance ladder probes physics today, 13.8 billion years later. The statistical framework for declaring them inconsistent assumes both are unbiased measurements of the same underlying quantity. But if the universe itself evolved, if the expansion rate genuinely changed between those epochs, then the comparison is not a test of measurement error. It is evidence for evolution. This is not a fringe position. It is, in fact, what those survey results suggest. If dark energy is changing, then the inferred Hubble constant from the early universe is a prediction based on an incorrect assumed future, and the late universe measurement is simply correct. Under this reading, there is no tension. There are 2 accurate measurements of a universe that evolves. The skeptic also raises a quieter concern: institutional incentives. Modern science rewards bold claims. A paper announcing potential new physics attracts citations, funding, and attention. A paper carefully demonstrating that systematic errors remain plausible attracts less. The community may, without intending to, have tilted its collective attention toward the dramatic interpretation. History supports caution here. The anomalous precession of Mercury stood for decades before general relativity explained it, and nobody proposed radical new physics in the interim. The solar neutrino deficit lasted 30 years before neutrino oscillations resolved it without requiring any new fundamental framework. Cosmological anomalies have faded before, but the skeptic must face the accumulation of evidence now. Gravitational lensing time delays. Using completely different physics, find a high expansion rate. Surface brightness fluctuations find a high value. Planetary nebula luminosity functions find 74. The agreement among local methods using separate systematic errors is difficult to dismiss as coincidence. The second skeptic is losing ground. Slowly, carefully, with appropriate humility, the community is moving toward a conclusion that cannot be blamed on statistics or assumptions. Something is genuinely different about the universe than our best model predicts. The next question is whether that difference is violent enough to end everything. There is a scenario at the edge of the baryon acoustic oscillation data that physicists find deeply unsettling. It does not end the universe slowly. In cold silence, it ends everything violently on a schedule. Standard dark energy behaves like a fixed energy density woven into space itself. As the universe expands, the amount of dark energy per volume stays constant because it is a property of space rather than a component filling it. This produces accelerating expansion, yes, but expansion that grows gently and predictably. Galaxies recede. The cosmic horizon shrinks. Eventually, the universe reaches heat death, cold and empty, and eternal, bleak, but orderly. Phantom dark energy is different in a specific and terrifying way. Its energy density increases as space expands. The more room there is, the stronger it gets. This is confirmed at the theoretical level to be a sign of negative kinetic energy, a field rolling uphill against every physical expectation. The mathematics allows it. Whether nature allows it is what the survey results are beginning to test. If phantom dark energy dominates the future, the expansion does not merely accelerate, it accelerates faster and faster, without bound, until the scale of the universe becomes infinite in finite time. That is not metaphor. It is a mathematical singularity. A moment at which all distances become infinite simultaneously, tearing apart every structure that gravity and electromagnetism and nuclear force had ever built. The timeline, worked out in 2003 by physicists Robert Caldwell, Mark Kamionkowski, and Nicholas Weinberg, follows a specific schedule, assuming a dark energy equation of state of roughly -1.5. Roughly 60 million years before the end, galaxy clusters lose gravitational binding and disperse. 3 months before, planetary systems become unstable as orbits decay into chaos. 30 minutes before, Earth itself explodes as the force holding its atoms together fails against the accelerating expansion. In the final instance before the singularity, atoms are torn apart, nuclear bonds dissolve, protons and neutrons scatter. Then the singularity arrives. This is called the Big Rip. The Dark Energy Spectroscopic Instrument Year 3 data, released in March 2025, found that when combined with the Dark Energy Survey supernova sample, the preference for phantom regime dark energy in the past reaches 4.2 sigma. That is not confirmation. It is a signal demanding attention. The result depends on which supernova dataset is used. Different combinations of the baryon acoustic oscillation measurements with different supernova compilations give different conclusions. Some favor phantom behavior in the past, transitioning to more standard behavior today. Some allow the cosmological constant as a viable fit. No single analysis confirms the Big Rip as our fate. But the possibility is now scientifically respectable. It is being calculated, modeled, tested, and taken seriously by researchers whose careers are built on exactness. The universe is not confirmed to be heading toward a violent end. The data are simply honest enough to admit that we cannot rule it out. The fate of everything remains an open question, and the instruments that might answer it are just now coming online. The answer is coming. We do not know what it will be, but the machines being built right now will force a reckoning, one way or another, within the next decade. The Simons Observatory sits in the Atacama Desert of Chile at an altitude of nearly 17,000 feet, where the atmosphere is thin and dry enough to observe the ancient microwave glow with extraordinary clarity. Its suite of telescopes began operations in 2024 and will measure the polarization of the cosmic microwave background with sensitivity that exceeds the Planck satellite by a significant margin. New constraints on early universe physics, neutrino masses, and the sound horizon are expected through 2026 and beyond. If early dark energy left any trace in the polarization signal, the Simons Observatory will find it. The Vera C. Rubin Observatory in Chile carries a camera so large it can photograph the entire southern sky every few nights for a decade. Its legacy survey of space and time will detect millions of supernovae, map billions of galaxies, and catalogue thousands of gravitational lenses. The sheer scale of its statistical power will reduce uncertainties on cosmological parameters to levels previously unimaginable. More importantly, it will catch supernovae at distances and redshifts that current surveys cannot reach, extending the distance ladder to new rungs and testing whether the expansion history matches lambda-cold dark matter across a wider range of cosmic time. The Euclid Space Telescope, launched by the European Space Agency in 2023, is already delivering results. It maps the large-scale structure of the universe through weak gravitational lensing and galaxy clustering, measuring how matter is distributed across billions of light-years. Its first data releases in 2024 provided new constraints on dark energy. Over its 6-year mission, Euclid will observe billions of galaxies, building a map of cosmic structure detailed enough to test every serious proposed solution to the Hubble tension. Perhaps the most independent measurement of all comes from gravitational waves. When two neutron stars merge, they release both a burst of gravitational waves and a flash of light. The gravitational wave signal encodes the distance directly through the physics of the merger. The light signal gives the redshift. Divide distance by redshift, and you have the Hubble constant with zero dependence on Cepheids, supernovae, or any other link in the distance ladder. The neutron-star merger detected in 2017 gave a first gravitational wave measurement of the expansion rate. The precision was low. The answer was consistent with both camps. Future events, detected by the upgraded gravitational wave network of LIGO, Virgo, and KEGRA, combined with electromagnetic telescopes tracking the light, will build a sample large enough for decisive results. The timeline is real. Within 5 years, the data will exist to either confirm or deny the tension at a level that leaves no room for ambiguity. The community knows this. The urgency in the field is not abstract scientific curiosity. It is the recognition that a verdict is approaching, and that whatever it says will reorganize everything. The universe has been keeping a secret. The instruments we are building are close enough to hear it. Behind the measurements and the sigma values and the telescope proposals, there are people. People who have spent decades on this problem, who have built careers around a specific answer, who have won prizes and written papers and trained students, and who now face a universe that refuses to behave the way they calculated it would. Adam Riess is perhaps the central figure in this story. He shared the Nobel Prize in Physics in 2011 for the discovery of accelerating cosmic expansion, the measurement that revealed dark energy and appeared to complete the Standard Model. That discovery made him one of the most decorated scientists of his generation. And then his own measurements of the Hubble constant began to disagree, year after year, with the universe that dark energy was supposed to inhabit. The irony is real, and he does not hide from it. The model validated by his Nobel-winning work is the model his subsequent measurements are now challenging. He has spent 2 decades defending results that grow more uncomfortable, not less, as precision improves. With measurement errors negated, he said to reporters in March 2024, what remains is the real and exciting possibility that we have misunderstood the universe. He says it with something that sounds like genuine excitement, but 2 decades of scrutiny, criticism, and accusation of systematic error leave a mark. Wendy Friedman's story carries a different kind of weight. She led the original Hubble Space Telescope key project that first measured the expansion rate to reasonable precision in 2001. When the tension emerged, she championed the tip of the red giant branch method as an independent check that might bridge the gap. Her results consistently found intermediate values, suggesting the crisis might be smaller than claimed. Then came March 2024. Her team unblinded their James Webb Space Telescope analysis and initially believed they had erased the tension entirely. A few weeks later, they found errors. A crowding correction applied twice. Larger uncertainties than expected. Correcting the mistakes pushed their values upward. The tension came back. Watching a result you believed in collapse under your own reanalysis is a particular kind of scientific pain. Graduate students are making career decisions under this uncertainty. Should they bet on lambda cold dark matter surviving and invest in refinements of the standard model? Should they work on early dark energy theories that face increasingly tight constraints? Should they pursue the new telescope surveys, betting that better data will crack the problem open? The stakes of choosing wrong are not trivial. A dissertation topic in cosmology is a 5-year commitment. A pivot to a dead research area can set a career back by a decade. The tension has also sharpened interpersonal dynamics in the community. The Riess team and the Carnegie-Chicago Hubble program teams have occasionally clashed publicly over calibration choices, data treatments, and the meaning of each other's results. Scientists are human. When two groups spend years claiming incompatible results, the debates acquire an edge that peer review does not always smooth away. This is how science works under stress. It is not tidy. It is not always civil. The pressure of an unresolved crisis pushes at the seams of professional culture, and somewhere in that pressure, the answer is forming. The measurements have been checked. The James Webb Space Telescope confirmed the distance ladder. The cosmic microwave background analysis has been scrutinized by thousands of independent researchers. Both camps claim precision below 2%. Both cannot be correct in the universe we think we live in. So what if the universe we think we live in is not quite the universe that actually exists? The cosmological principle is the bedrock assumption underlying every measurement discussed in this documentary. It states that the universe is homogeneous and isotropic on large scales. The same physics applies everywhere. No special locations, no preferred directions. This assumption allows cosmologists to treat a local measurement as a global one, to infer the expansion rate of the entire cosmos from observations made within a tiny corner of it. It has never been confirmed. It has been tested to the limits of available surveys, and the tests have passed. But the limits of available surveys extend to only a fraction of the observable universe. Beyond the reach of current instruments, the cosmological principle is an assumption, not an established fact. This is where the local void hypothesis enters. The Milky Way sits inside a large underdense region, a bubble of below-average matter density roughly 300 million light-years across. In standard cosmology, such a void would cause local expansion to proceed slightly faster than the cosmic average, exactly as observed. If we are measuring the local expansion rate and comparing it to a model calibrated to the global average, we might be comparing two genuinely different things. The void is real. Its existence is confirmed by galaxy surveys. What is disputed is its size and depth, and whether it is unusual enough to explain the full magnitude of the tension. Some analyses find that it does, others find it falls short by a meaningful margin. A completely independent modified gravity theory, modified Newtonian dynamics combined with sterile neutrinos, proposes that the void plus altered gravity can simultaneously explain the tension, the structure of the local universe, and several other anomalies in a single framework at roughly 1% confidence level. These proposals are not mainstream. They are being tested against new data, and so far no single alternative has cleared every hurdle. But their existence reflects something important: the willingness of serious researchers to question assumptions that have been comfortable for decades. The history of cosmology rewards that willingness. The expanding universe was considered metaphysical nonsense until the data forced acceptance. Dark energy was derided as a fudge factor until it earned a Nobel Prize. The ideas that reshape science often begin on the edge of credibility, defended by small groups against a skeptical mainstream, until the evidence becomes undeniable. Something in our model is wrong. The measurements confirm it. What is still open is which part of the model carries the flaw. Is it the physics in the early universe? The late universe? The assumption of uniformity? The interpretation of redshift itself? The answer is in the data. We just have not been asking quite the right question. The universe is 13.8 billion years old. We have been measuring its expansion rate with genuine precision for less than 30 years. Every telescope ever built has looked at one sky, around one star, in one galaxy, at one moment in cosmic time. We are trying to understand everything from the vantage point of almost nothing. The Hubble tension might be the first serious reckoning with what physicists call model fragility. Lambda-cold dark matter is not merely a description of observations. It is an extrapolation from a finite set of measurements made in one region of one universe, assumed to apply everywhere and always. For 6 decades, every new observation confirmed the extrapolation. It became easy to mistake consistency for completeness, but consistency has limits. A model can correctly predict every observation within its domain while being fundamentally wrong about something it has never been forced to test. The history of physics is full of this pattern. Newtonian gravity correctly predicted the orbit of every known planet for over 200 years. Then Urbain Le Verrier noticed a tiny discrepancy in Mercury's orbit that Newton's equations could not explain. That discrepancy required general relativity to understand, and general relativity revealed that Newtonian gravity was an approximation, correct within its range, incomplete at the boundary. Lambda-cold dark matter may be in that position now. The Hubble tension is a discrepancy in the one parameter that tests the model's internal consistency across cosmic time. It may be pointing toward an approximation boundary, a place where the assumptions baked into the model are no longer valid and where the deeper physics begins. What lies beyond, we genuinely do not know. This is the honest answer, and science is built on the courage to say it clearly. Early dark energy is the most studied proposal, and it is failing observational tests. Modified gravity theories have not yet passed all the constraints. Evolving dark energy from the survey is real and statistically significant, but its implications are still being worked out. Gravitational wave standard sirens are promising but require more events to be decisive. The uncertainty is uncomfortable. Humans prefer explanations. We build institutions, fund careers, and write textbooks around our best current answers, and we become attached to those answers in ways that can slow the recognition of their limits. The Hubble tension has been resisting resolution for nearly a decade. That resistance is not a failure of science. It is science encountering the edge of its current reach. Epistemic humility is not weakness. It is the prerequisite for every genuine discovery. Every major advance in physics began with someone willing to say that the existing explanation was insufficient, despite the social and professional costs of that admission. The researchers working on the Hubble tension today are doing exactly that work, carefully, rigorously, with instruments that would have seemed miraculous to every cosmologist who came before them. The universe is speaking. We are learning, slowly, how to listen, and what it is saying will change everything we thought we knew. We are back where we started. 2 telescopes, 2 methods, 2 answers, 1 universe. The Hubble constant, 67 from the early cosmos, 73 from the late cosmos. The gap is confirmed at 5 sigma. The probability that it is a statistical accident is less than 1 in 3.5 million. The James Webb Space Telescope has ruled out every known measurement error at 8 sigma confidence. Multiple independent methods using completely different physics all find the same high value in the local universe. The cosmic microwave background continues to insist on the low value, with half a unit of uncertainty, built on 6 decades of confirmed predictions. Something is wrong, and nobody can explain why. In 2024, Adam Riess stood before cameras after the James Webb Space Telescope confirmed his measurements for the final time and said, "With measurement errors negated, what remains is the real and exciting possibility that we have misunderstood the universe." That sentence deserves to sit with you for a moment. A Nobel laureate, the person most responsible for shaping our understanding of dark energy, the scientist whose life's work helped build the most successful predictive framework in the history of cosmology, looking at a dataset and saying, "We misunderstood the universe." This is what science looks like at its best, not triumphant, not certain, honest. The Dark Energy Spectroscopic Instrument has mapped more than 14 million galaxies and found hints that the dark energy driving the acceleration is changing over time. If that signal strengthens, The cosmological constant is dead. The force governing the expansion of everything is dynamic, evolving, and still in motion. We are not observing a fixed cosmos. We are watching something ongoing. Early dark energy, the leading theoretical solution, is failing. Modified gravity has not yet found its footing. The sound horizon crisis has no accepted answer. The age of the universe, under a high Hubble constant, presses uncomfortably close to the age of its oldest stars. Every proposed resolution creates a new problem somewhere else. But there is something in that cascade of failures that points toward a genuine revolution, not a refinement, an actual revision of the framework at the level where Newtonian mechanics gave way to general relativity, or where a static cosmos gave way to an expanding one. Those transitions did not come with warnings. They came with anomalies that grew louder over time until the old framework could no longer hold them. The Hubble tension is louder than any cosmological anomaly in living memory. We live at an extraordinary moment. The instruments exist. The data are accumulating. The Simons Observatory is mapping the ancient microwave sky. The Rubin Observatory is photographing billions of galaxies. Euclid is charting the large-scale structure of the cosmos. Gravitational wave detectors are collecting new standard sirens. Within a decade, the uncertainty about which model is correct will narrow to the point of decision. The universe began with something, expanded through time, built structure, lit stars, assembled galaxies, and produced, in one unremarkable corner of one average galaxy, beings curious enough to measure how fast the whole thing is moving. And the whole thing is moving in a way we cannot yet explain. That is the most exciting sentence in science. The universe is expanding wrong, and the greatest discovery of this century may be the answer to why. We are just beginning.